Hello, my name is Jong-Hyun. I'm PhD candidate in the University of Arizona. The title of talk is the reinforcement running for automated reinforced concrete structural design. Before we begin, I'd like to give you an overview of this work. The goal of this research is to make an artificial intelligence structural designer who can design reinforced concrete structures automatically. I'm going to start to introduce why we use reinforcement running for structural design, and I'll move to a case study on reinforced concrete beam design. Structural design is a major part of construction project. Automation of structural design has been in huge interest and various optimization methods have been widely tried for structural design automation. There are also some classical machine learning methods have been tried. However, they have not used in practice because of several limitations. Still, structural design process is being rely on the designer's experience and their trial and error process. Here are the limitations of optimization and machine learning based method. The optimization required excessive and iterative computation as search space increases, and every case requires such iterative process. Sometimes optimization needs each parameter tuning to make sure the stability, and machine learning based method requires excessive handcrafted design examples for supervised training. That is very labor intensive in reality, and they don't guarantee the optimal designs. We propose to use the framework of reinforcement running for structural design, where an agent takes sequence of actions and interaction in the environment and gets periodic feedback in the form of rewards. And over time, the agent runs from these rewards in order to take optimal decisions. You may know about the AlphaGo, the deep reinforcement running based agent surpassed world-class Go players and shows feasibility to apply for various complex engineering domains. So in this work, we train an agent a variety of design cases by reward to make him as a human expert level structural designer. So I'll go into detail later some more. There are two main advantages of reinforcement running for structural design. It does not need any optimization procedure once the agent is trained, and it does not need any labeled data for training because the agent is trained by reward. Here I listed the main contributions of this study. We first time ever investigate the reinforcement running for structural design automation. Reinforced concrete beam designing task was modeled as Markov decision process format as state, action, and reward. And we developed a Python-based RC beam designing environment for agent training. And we designed the reward functions to guide agent to run RC beam designing tasks over a variety of design conditions. And we developed a convolutional neural network-based actor critic network. And we validate the performance of trained agent with 100 design cases. And we compared performance with human expert design examples and optimization method with a building example. The goal of this study was to train an AI agent to design RC beam automatically having 15 to 30 feet length and 40 to 945 feet K moment capacity with a self-weight with satisfying all core requirement of ACI 31814. This is a typical design range of building frame. For each design case, the agent was allowed 5 design trials. In the first step, the agent only see beam length and MU without self-weight and do first design trial. The initial design trial cannot consider self-weight effect because we don't know how much weight should be calculated before we decide the dimension. After that, the agent can observe previous design details including MU with self-weight and move next design trials. But after training, AI agent will aware how much weight will be applied by action from his experience. So the agent generate 5 design cases and a best design case with the most economical with satisfying all code requirement was selected for actual use. This is how we define the design problem in reinforcement learning format. The state has the component that agent observe and it includes many design details like dimensions and lever size and quantity, MU and FNM and code criteria checks. And we design the agent to decide 5 design parameters by actions including beam width, depth, lever size, quantity, and strop size. The environment does design calculations and check whether it is good or not based on the ACI 318 and calculate material cost and reward. The reward functions are modeled when any cost violation is occurred, the agent never get positive side reward. And when the design satisfies all requirements, the agent will get positive side reward. Ultimately, the agent will try to avoid code violation and design in economical way. This is the basic design condition that I defined. I consider the material cost for concrete and steel rebar taken from a literature. This case is based on the ACI 318, assuming concrete strength as 4 KSI and rebar as 60 KSI. I considered all ACI design code requirement for practical use, so I considered total 9 design constraints. For shear strobe arrangement, we split it two strobe regions. The agent only selects the size, but the strobe will be arranged automatically by deterministic way based on ACI equations. This is the detail of the design parameters, which is practical range that agent uses. They're decided based on the defined possible design parameters within loading range. This is the detail of the reward. In the reinforcement learning application, the reward is very important for proper agent training. The negative reward will be given when any code violation happened. The negative reward functions are formulated using 7 design criteria and made into normalized linear functions and multiplied by weight. You can see this plot that linear negative reward functions will give more negative reward when the level of code violation is high. When all code requirement is satisfied, the agent is able to get positive reward according to material cost. However, the optimal material cost varied by length and moment capacity requirement. We need to define generalized baseline price per design case in the function of beam length and moment capacity. So I formulated near optimal price function to define cost reference for a broad range of beam lengths and loading range. I made 12 handcrafted design costs for different loading and beam lengths and made set of linear functions. Finally, this function predicts near optimal price approximately by the function of beam length and design moment requirement. Now we can estimate approximated optimal price from any loading condition and beam length. I modeled the positive reward function as a linear function again. The agent started to get reward when the designed beam price is within 125%, and it will get more reward as the price is cheaper and cheaper. We selected the agent as deep deterministic policy gradient called DDPG, which has multiple continuous action dimension, which can handle height, depth, rebar size, can be chosen separated at once. It has 4 distinct features, including noise for exploration, replay buffer, soft target update, and actor critic network. Particularly, we used the annulled action noise for huge exploration in early training stage, but used just 1% of action noise later for maximal training efficiency. This is the actor critic network that we designed. The network has same architectures for actor and critic networks that is consists of 8 layers of 1D CNN with LERU activation. The agent was trained with 100,000 randomly generated design cases. The left figure shows the reward variation over training procedure. The right figure shows the design success rate every 100 cases. Initially, the agent acts very randomly because it doesn't have any idea about designing, but over time, you can see the negative reward decreases and success rate increases. After 15,000 episodes, the agent started to success the design without code violation, and over the performance increased and stabilized. The trained agent's performance was tested with 100 cases, which have loading range 96 to 702 k-feet with random span lengths. Left axis shows a reward per cases, and right axis shows a relative cost ratio to near optimal cost from the cost function. All the cases succeed to design with 125% of near optimal cost, and many of cases you see that exceeds 10 reward, which means they did a better job than defined near optimal cost. Here is the detail of some design cases. As you see, all the designs had minimal moment margins shown in the red box, which are good quality. Case 44 and 75 are the worst case among 100 cases. But as you see, the design qualities are still good as they designed within 125% of desired cost. This is a complete design example from agent generated. All details required for design were considered. Here I compare the agent performance with human designer. I took examples from a design guidebook and compared the design result. The trained agent showed less material cost, showing in red box by preferring to use less quantity of rebar but more slender beam design. We also compared the building design example with optimization method. For this case, the negative moment was used for governing moment capacity for rebar arrangement by agent, but positive moment in your column was arranged by minimum requirement by ACI code. It was not possible to exact comparison because the column design was out of scope. For this case, former cost was also considered and old design code ACI 31899 was used, so we retrained the agent using same strategy. The genetic algorithm and Big Bang Big Crunch algorithms are used for comparison. The table summarizes the design result. Our method shows a comparable material cost to the optimized design result. The optimization method required huge number of iterative analyses to achieve these design results. However, our proposed method generated the design instantly within just 5 trials, which is way more efficient but similar material cost. It is not exact comparison as our method doesn't cover column design, but we can find that the distinct advantage of reinforcement running based structural design method over optimization method in terms of computational efficiency. Here we conclude by summarizing this study. RCBeam design task was formulated in reinforcement running format. We designed reward functions to encourage the agent to avoid code violation but design economically. And we designed 1D CNN based actor critic network, and the trained agent was validate its performance via 100 design cases, parametric study, and comparative studies. And the proposed method showed great performance and feasibility for automated structural design. The future work will be extended to different type of structures and global level structural design automations. Thanks for watching.